Please note that this is a sponsored event and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors and pricings of products and services. And now, welcome to Designing Your Next HDPE Project. I am thrilled to welcome back our valued partners for the 5th consecutive year of HDPE sponsored webinars with ASCE. This is the first of 4 exciting webinars in the 2025 series, generously brought to you by the Alliance for PE Pipe, Modern Polymer, and Core & Main. Each webinar in this dynamic series will deliver 75 minutes of invaluable content. And now I'll turn things over to Peter Dyke, Executive Director of the Alliance for PE Pipe. Welcome, Peter.
Hey, Robin. Thank you so much and for welcoming us back to another year of webinars with ASCE. You know, you guys do a great job. And to our audience, I assure you, Robin is a real person. She exists and she's fantastic and she works really hard behind the scenes to bring these webinars to you. So let's hear it for Robin. Robin, thank you for all you do. And we're very thankful to ASCE and to your audience today, the engineers that are listening in, the EITs, the new graduates, and the old salty veterans. We thank you for trusting your time to us at the Alliance for PE Pipe for bringing this content for you for our 5th year. And Robin, that's how I know how long COVID's been hanging around, because we started in that first year of COVID. The Alliance for PE Pipe is thankful for its many members. These are the companies that contribute financially to our efforts this and every year. Without them, we couldn't do what we do. We bring this free content to you in a webinar format 16 times a year, and 4 of them are through ASCE this year. So let's hear it for these companies that help fund our not-for-profit organization. We are an educational organization. We have fun with social media. We post announcements like, hey, this webinar is coming up. We're posting a podcast in social media tomorrow. We've got a very cool podcast that Dan Landy, Richard Kloss, and I did with Adrian Hanam, who's an expert in marine applications. So look for that coming out tomorrow at our podcast channel, also on our YouTube page. And this is the slide that Alan Ambler hates to prepare every time we do a webinar because it always changes. But Alan, thank you for making this one correct. But these are all the events that we have coming up, Alan, in the next 3 weeks. We're a pretty busy group of guys.
I'm aware, Peter. Yes, I work with you. We are very, very, very busy. There's lots of things that happened. COVID really afforded us a great opportunity to either pivot or get out of the way, and we pivoted. So, in typical Friends fashion, you pivot. That's what we're going to do, and here we are showing you some more information. So, good job, Peter. We really appreciate it.
Yeah, so we do all these road shows. We do Spec and Tech. So if you're in one of these regions and you see a road show, then there's a Spec and Tech. What's the difference? The road show is a truck with 10,000 pounds of gear and a bunch of experts. The Spec and Tech is 5 hours. You drive the program with your questions. You bring your spec and let's talk HDPE tech. All right, Alan, go to the next slide. I can talk all day about our programs, and I just thank you all for listening. We also have prepared by our engineers a litany of free resources. We'll edit a spec for you free of charge. Just send us a message in Q&A and tell us what you need help with. We'll help you with project reviews. We do not charge for our service. And we also have something called a engineer's package, which is a free document that is available to you. It's time to update it, Alan, but it's been hanging around for a while. And actually, we don't say that it's the 2003 version or say, we just keep updating it all the time. We also have case studies on our website and standard details available to you in AutoCAD. So Taylor Holliday and Dave Mosier, please come on and introduce yourselves. Let's start with you, Taylor Holliday.
Hey, Peter, thanks for introducing us. Really excited to be here and help promote the PE Alliance and help in any of the webinars we can. Modern's an extruder based in Houston, Texas, and we manufacture polyethylene HDPE pipe for our distributors and for the whole P Lines network. So we're glad to be here today, and thank you for having us as a sponsor.
Well, thank you for doing it. You're a new sponsor, and we thank you for stepping up and being with us all year long, Taylor. So we look forward to learning more about modern polymer, and you've got one of your guys on the bench today. So
Yep.
thank you for your support. Dave Mosier, Core and Main, back for your 5th year.
Yeah, thanks. Thank you, Peter. Excited to be here today, and thank you for the invite as well. For those of you not familiar, Core and Main is one of the country's largest distributors of pipe valves and fittings for water and wastewater transmission lines. We're very excited. We work in PVC and ductile iron, but we're very excited about polyethylene. We've got 350 locations across the country. We pride ourselves on providing local service nationwide. And when it comes to polyethylene, we're especially excited about today's topic because as it's very important to bring a distributor partner in early in your project. We can help you understand what's possible with polyethylene. We can help your contractors bid it more correctly, and then we'll stay with the project all the way through installation to make sure it's done and successful.
Yeah, that's for sure. You are, central to our mission as we work through our contractors. Every one of these, through our distributors, every one of these webinars we do with a company like yours, Dave. So thank you for what you do to support the Alliance and also to support the market. So great job. All right, Alan, next slide, guys. Thank you very much for being here, and please participate on the bench. So we also have speakers today that are helping Alan Ambler, and they are Doug Keller and Richard Kalasa. Doug, please introduce yourself.
Thank you, Peter. I want to say good afternoon, good morning, and good evening to those of you attending, depending on where you are in the world. My name is Doug Keller. I'm a technical service engineer for LyondellBasell, and we produce polyethylene and polypropylene resins that are used in multiple applications. But today, I'm going to be focusing on polyethylene and pressure pipe applications.
Yeah, good for you, Doug, and we appreciate LYB's support. Richard Klasa, please come on and introduce yourself.
Hi, good afternoon, good morning, and good evening, depending on where you are in the world. Thanks, Doug, for that. Yeah, again, I'm just happy to be here to support the Alliance, and thank you again, Modern Polymers and Core and Main for sponsoring these events. They are outstanding, and I hope that the things that you learned today are beneficial and add a whole bunch of value to your repertoire of engineering.
Yeah, thank you, guys, and we'll see you shortly. Also active behind the scenes in this webinar, we have over 600 people on this call today. We have what we call the bench. You are permitted, and we encourage, actually, to ask any polyethylene-related question. And this group of guys, all guys today, no gals today, will answer your questions. So please contact those guys by using the Q&A function, not the chat function. Dan Landy, would you mind coming on and telling our audience how they obtain their CEU or PDH?
Yeah, I don't know if I have my lighting all set up. Sorry about that. But there is a survey at the end of the webinar. Please leave your information there, and I will get out to you, just like Robin said, in about a week.
Yeah, so Dan, they have to stay through to the end, correct?
Correct.
Okay, so that's 75 minutes, 60 minutes from now. Alan, you're up.
Peter, I'd like to just opine that we already have multiple questions within the Q&A. So they get it. They know what's going on, Pete, and it's pretty cool, the function as to which we answer those questions behind the scenes as organized by you. So way to go, Pete and Dan and Stephen Boros and everybody else on the bench. Thank you so very much. We really appreciate that. And keep asking those questions, everybody.
Yeah, so Q&A, and that way we can keep track of it and then turn them over to Dave Mosier when we're done. All right, next slide. So these are all, you may want to take an image, take a shot of this. This is how you can contact each and every one of us. Pick the guy you want to talk to, and we will communicate with you about your issue. Any poly-related question, you are encouraged. With that, I'm going to turn this over to Doug Keller, who's going to cover the material. So Doug's focus is going to be on the resin that goes into the pipe and then the pipe itself. Thank you, Doug. I'll fade off into the background. Best of luck.
All right. Thank you, Pete. Thank you, Alan, for advancing the slides. So where does polyethylene come from? Typically in the United States and in North America today, we are sourcing the raw materials to make polyethylene from the wellhead. So when we go drilling or fracking for oil and gas, the gas portion is what we are using to produce polyethylene. So the oil goes to the refineries. Out of the gas portion, which is methane, propane, ethane, butane, the methane is what goes to your house for heating and cooking. We take off the ethane. So we take that ethane to a step called distillation, where we purify it and make sure that what we have is pure ethane. We then go to a step called cracking. Cracking is where we take the ethane, we open it up and create a double bond between the two carbons that are present in ethane, turning it into ethylene. That ethylene is then introduced into our polymerization step. In the polymerization step, we use a catalyst in combination with heat and pressure. We open up that double bond and we start to link those ethylene chain or monomer units together to create polyethylene. So polyethylene is many little ethylene units. So you can think of it as a chain link where each link is an ethylene unit. We're making varied molecular weights depending on the application that we're going after. That comes out of the reactor. We separate it off from the reactants that weren't reacted and goes into our pelletizing step. In the pelletizing step, we add the additive package that is needed for the particular application, and we produce pellets. If you've ever had a Beanie Baby explode on you, those are those little pellets that are inside. So they're about the size of a BB, maybe 4 millimeters in diameter, sometimes cylindrical, sometimes spherical. We load those materials into a rail car. The majority of polyethylene is shipped to our customers in rail cars. Rail transport is an extremely efficient way to move polymer around the country. When it gets to our customer, they then unload, they check the material and make sure that what they received is what we should be sending them, load it into their pellet silos, and then they go through the pipe extrusion step. Now, Alan, if you can go to the next slide. This is kind of an old schematic of a polyethylene pipe production line, but way on the left, in the upper left corner, you see the extruder. It's somewhat hidden. In that extruder, we have a single screw that is turning. It is using frictional heat to take those pellets, melt them, and form them into a stream of material coming out of the die. That then goes into the vacuum tank where it is sized. Most polyethylene is sized to the outer diameter of the pipe. So we have a certain fixed outer diameter that we're looking at. And then we can adjust by changing the die setup, how thick the pipe is and what the diameter of the pipe is. It then goes into secondary cooling tanks. So we're trying to take that heat back out to solidify the material. It is being pulled by the pulling head or the pulling machine once it comes out of the die. We go through wall monitoring to make sure that we're making the diameter and the thickness that we need. And then the pipe is cut in whatever lengths that you need. So we can supply pipe in stick form, which is typically 6-inch diameter and above, or we can also provide it in coil form, which is 6-inch and below, depending on what your application is and what your end use for the material is.
So, Doug, this gets bigger, right? When we get into larger pipe, because we've been talking about larger pipe for a while. I mean, this stuff gets pretty darn big, doesn't it?
Yes, it does. So these lines can be 150 to 200 feet long, to give you an idea of how long they are. And then you have, say, an additional 40 feet or 50 feet, depending on the length of the stick that you're producing beyond that. So these plants tend to be several hundred feet, 250, 350 feet in length, with multiple production lines in each facility.
All right. So the process is the same. We're just taking the resin and making sure that it meets the parameters that are necessary in order to be able to melt HDPE and fuse it together. And now we're just getting bigger. The same thing that we would see through butt fusion, through electrofusion, through sidewall fusion, through any type of fusion.
Exactly.
Awesome.
All right, next slide. So when we talk about plastics, there's two general, can you go back one, Al? There we go, thank you. There's two general categories of plastics. So think of this as metals. You have your ferrous metals, you have your copper metals, you have your aluminum metals. So in plastics, we have thermoplastic materials, which is like polyethylene or polypropylene, as you can see from the pipes there in the image. A thermoplastic material can be repeatedly softened by heating and then hardened by cooling. So what this allows us to do is to take those pellets that are cold, heat them up, make pipe, send the pipe to you. We then fuse the pipe together by heating it up again, cooling that joint down, and now you have a monolithic piping system. So it is reversible and repeatable. The polymer maintains all of its physical properties during this melting and cooling phase. So there's really no change to the polymer in the number of times that you would typically expect for heating and cooling to occur. So typical thermoplastics, as I said, polyethylene, PVC is a thermoplastic, polypropylene, and then the polyamides, which includes nylon, are also thermoplastics. On the other side, we have what's called thermosets. So this is a material that when it's heated up, it has a chemical reaction that occurs called the curing process, which turns it from a material that can be heated to a material that can't be heated and reformed again. So it changes the mechanical properties and the material properties of the polymer. So as I said, it's irreversible by application of heat. And in the piping world, this would be something like an epoxy fiberglass reinforced pipe. So I'm not going to name the name, but you know who I'm talking about. Those are typically stick pipe that have some type of a mechanical gasketed joint because you cannot heat them up and fuse them back together. On the plumbing side, PEX or cross-linked polyethylene would be another example of a thermoset material. Next slide, please. So when we talk about the material and we talk about fusion, I want to point you to this example here that we have on the screen. This is multiple thin sheets of polyethylene that have been laminated together and then put through the butt fusion process. So when we talk about material flowing out into the joint, here you can really see exactly what is happening to the material when it's heated and when we apply pressure to that fusion joint. That material is spreading, and as it spreads, it allows that joint to be formed. Next slide. So this is a video of the fusion process. Here we've heated the material up, we've created a bead. We're removing the heater plate, and now we're bringing the pipe ends back together, and you're going to see the fusion bead form. See how that material is flowing up and out, and on the inside it's flowing out and down to form the fusion bead. So this is what can be done with a thermoplastic material that can't be done with a thermoset material. Now, I don't recommend quickly removing the bead like they did in this video. There is a cooling step and things that we have to go through, but it's that thermoplastic properties that allow us to fusion to occur. So what happens during the heat fusion step? Well, polyethylene is a semi-crystalline material. For high density polyethylene, it's roughly 60% crystallinity, and the crystal section is a regularly ordered crystal structure. So it's very similar to metallics that have a crystal structure to them. In between those crystals, which is the little loops that are kind of tightly packed together, we have amorphous material. And I have an example here. If you think of these black and white sections as the crystalline phase, and then if you can kind of see there's Velcro here, that would be the amorphous phase. So what the amorphous phase does is it ties those crystals together, and it has a certain give to it that allows for some of the properties that we'll talk about in some additional slides. So when we go to heat up the material, as we heat it up in that fusion zone, for example, the crystal structure is erased and the material becomes very amorphous. So there's no general structure to the material. When we bring those surfaces together and now we allow it to cool, obviously we're having material that's flowing in the joint. And as it flows, those chains basically start to entangle with each other. And as it cools down, we now reform that semi-crystalline structure. And so you can see in the last picture, now we have a semi-crystalline structure that resembles the two single pieces of pipe, but that semi-crystalline structure is across the whole joint. Alan, you have a comment?
Richard Colassa, I know that you are just chomping at the bit to try to opine here. So yeah, you're just right there. I mean, this is all up for you. Come on and tell us what you think.
Yeah, Doug, you described it beautifully. But really what this means is we become monolithic. So I know Doug mentioned a joint, but it's really not a joint. It becomes now part of that same structure. So that's why we find um, the fusion process and the area of the interface where these molecules come together and combine actually provide a stronger element. And to my opinion, it's because that process is fairly slow in cooling. And so like a pipe, when we rapidly cool it and pull that heat out of there, we can affect how that crystallization forms. But when it slowly cools through the fusion procedure, it actually becomes a little bit more dense. So it becomes stronger than the parent pipe. And I can tell you with a high degree of confidence, I've done thousands of tensile pulls on various properly fused joints, and I've never had one fail in the joint. It's always failed in the parent pipe. So whether that adds to thickness, and that's bead removal as well, but it just goes to show that monolithic system does exist.
So everybody out there on the call, by the time that we handle HDPE properly, so we get back to virgin resin material, we get back to the proper handling procedures with the right temperatures and the right time to be able to put this pipe together. It doesn't matter if you're extruding it, if you're butt fusing it, if you're electrofusing it, it's all the same. And that's one of the beauties of HDPE is the fact that we are now controlling the flow of these molecules, as you see, across that element and that surface. And now we're getting back to a monolithic structure, as Richard said. So thank you, Doug and Richard, and keep going. I'm sorry to interject.
Okay, next slide, please. All right, so I talked about semicrystalline before. Again, the crystalline regions give the material its density. And density is related to the tensile strength of the material. The more dense the material, the higher the tensile strength, the higher the stiffness of the material, the more chemical resistance you have. If you think about, if you're a chemical and you want to get through that image on the left, that's a pretty tortuous path. That's like driving through New York City. However, on the right, if you're a chemical and it's all the amorphous, it's pretty easy to get through. That's like driving through West Texas. So the balance of these two properties is what gives polyethylene a lot of its properties and its advantages over some of the competitive materials like metallics, PVC, and other plastic materials. So again, think of it as being semi-crystalline and think of it being as a benefit. So when we have a semi-crystalline material like polyethylene, we have what's called viscoelastic behavior. So depending on the force applied and how long it's applied, the material will respond differently. So if you take a sledgehammer to a polyethylene pipe, give it a big whack, the sledgehammer is going to bounce back. Hopefully you're not directly in front of it. If, however, we are applying stress over a longer period of time, so say in a 10-hour range, where we're doing a hydraulic directional drill and we're pulling on that pipe and that pipe is under tension, its modulus of elasticity, its stiffness will decrease over time. So it depends on the duration of the load. Now, I know you're looking at this going, yeah, but I want to design for a 50-year, 100-year service life, Doug. I want 150 years of service life. Does that mean that my stiffness has basically gone down to 20% of what it was when that pipe was basically sitting on the ground waiting to be installed? No. When properly buried, the amount of force and the crown and the arching effect that we have of the soil, the amount of force that's actually on that pipe is about 1 to 2 psi. So if properly installed, this pipe is really seeing no type of backload, even if we're talking about 25, 30 feet of depth of cover. for the material. Alan?
Absolutely. So I will mirror that the external loading that the pipe sees in an open cut construction scenario is exponentially lower than anything that might be there pressurized internally. And that's fairly significant. And we'll get that there a little bit later as well. But yeah, definitely a great point, Doug. Thank you so much.
Yeah, and it does add to, you know, when we look at design, which we're going to get into, you know, some people might think, or engineers that I've run into, you know, bigger number, the better it is. Not necessarily, because what you're going to see from this is really aspects of designing for the system. And I think that that's more important than, and longevity, especially life expectancy when you have ductility versus brittleness. I mean, it makes a big difference. And even when we test to establish the pressure rating of our products, we're looking for that difference and that event to occur, going from ductility to brittle, because that changes the whole behavior of how that design would work. So it's really important that this is understood. I think this is one of the most challenging areas for design engineers to kind of comprehend, but you have to have faith, and learning about it. The more you learn about it, the more you'll understand it. And from Doug's perspective as a polymer design aspect, I mean, this is what they're building these polymers to do. And it's really, really important that we take advantage of those design aspects.
Yeah, and the other thing is we'll talk about surge allowance in a little bit, but the benefit of polyethylene is that elasticity that it has. So when we have a surge event come down the pipeline, it's basically going to cause that pipe to expand. Well, the pipe, because of its elastic properties, will stretch a bit like a rubber band and basically allow the pipe to absorb some of that energy from a surge event. So that's why we have significantly better surge resistance than other materials, because of that elasticity that we have inherently in the polyethylene molecule. Next slide, Alan. So a little bit more on viscoelasticity. So we use silly putty as an example. So silly putty is a polymer. It's a very low molecular weight polymer. You know, if you take a ball of silly putty and you basically sit it on the counter and let it sit, after about 5 minutes, it goes from being a ball to being kind of a lump or a patty. And that's creep. So all plastic materials will creep over time. Now, from a design standpoint, it's not something that you need to be concerned about. Because again, a properly installed pipe, whether it be above ground or in ground, is going to be supported so that creep doesn't become an issue. But it is that elasticity, that viscous flow, it's a viscous flow over time that occurs. But the benefit of polyethylene, as we talked about, is stress relaxation. So here you'll see a video of a pipe being pulled into place. So they're going to do a horizontal directional drilling, and we're curving it through a standard intersection, T intersection in a neighborhood. So in this case, we have basically a dirt berm and then also a mini skid loader that is allowing us to direct the pipe. This allows us to pull the pipe in. The video on the right basically shows that viscoelastic behavior, that ability of the polymer to take short-term loads by being lifted up and then pulled down as part of into the entry pit for a horizontal directional drill. So that's that benefit of the material. This is not something that you could do with any type of a metallic system. You could not do this with a PVC bell and spigot system. So that's that unique benefit of polyethylene in the real world installation. Richard.
Yeah, and just to point out, I mean, we talk about creep, so I think the first thing that comes to people's mind is deformation. This pipe is not deforming. Under those conditions that we understand the min bend radiuses and all those aspects of that viscoelastic behavior, you're not affecting the wall, you're not affecting the OD if done properly to the specifications that we require. So it's not a deformation aspect, but it's just a temporary situation for installation that really helps you benefit efficiencies in installation, especially in trenchless technologies.
Yep. And if you go past the bend radius, you might kink the pipe. If you kink it, cut it out, fuse it back together, keep going. So when we talk about material designation, what do we want to see on the print line? First off, you want a pipe with a print line. Never, ever, ever, ever accept a pipe without a print line, because you don't know what you're getting. It's like the can at the grocery store that's 25 cents because the label fell off. You don't know what you're getting. Is it beans? Is it succotash? You don't know. Got to have a print line. So what the print line will tell you is it's going to give a material designation and a cell classification for the material. So we have a classification system in ASTM, which gives us this cell classification that I love, a PE 445574C, which is a black PE 4710 pipe. However, not being a numbers person, you may just know it as PE 4710. That is the latest, newest material on the market, giving you the highest properties that you can find for a polyethylene material. So any print string that you're going to see should have a PE 4710. And for water applications, it will then be followed by a CC3, which is chlorine categorization. And we'll get to that chlorine categorization in a couple of slides. But always make sure you read that print line. Make sure that you're getting what you expected when you ordered that pipe. It will tell you the pipe size. It'll tell you the pipe thickness. It will give you the pressure class. It will tell you when it's made, who made it. And that print line is traceable all the way back to my material through the pipe manufacturer. So it's always good. If you have an issue, we need to know that print line should you have an issue. So what does PE 4710 mean? Well, PE is polyethylene. The first digit refers to the density. As we talked about, density controls our tensile strength, our stiffness. It also is a controlling factor for our pressure class and our pressure rating of the material. The second number is the slow crack growth resistance. So this is a test that we perform in the laboratory at elevated temperatures. The minimum value for a class 7 is greater than 500 hours. Now, most of the material, and we'll see on the next slide, is well above the 500 hours. And then the 10 refers to the hydrostatic design strength of the material. If you could go back a slide, Alan. That 10 is 1,000 PSI, so that includes our design factor, and that's where we start at when we start our design with the PE 4710 materials. We start at 1,000 PSI of tensile stress on the wall, and then we adjust that depending on pipe thickness, the applications that it's going into. Richard, I see you popped on.
Yeah, so just, and this is really an important aspect, because at the first slide that you showed about where polyethylene comes from and everything, there's lots of different reaction methods to make different polyethylene. So this is specific to pipe grade products. And as a pipe manufacturer, we also have to make sure that Doug or whoever is supplying the resin to us is sending us the right product. So we have to check it. So it's really our regulation aspect to make sure it's going to perform to the expectation that we're going to talk about.
Yep. Alan?
So Doug, I just noticed that your goatee is probably stronger than mine. I need to comb this and do other things for it as well. But this that we see here with 1,000 psi is actually has a caveat already. So it's already conservative in its function, because the ultimate tensile stress is 3,500 to 4,000 psi for HDPE pipe for the tensile yield. Is that correct?
Correct. So what we're looking at, again, that's the viscoelastic behavior and the effect of stress upon time. So when Alan talks about the tensile stress, that tensile stress, when we run a tensile test, is basically applied over several minutes, maybe 3-4 minutes, 10 minutes at the most. And so when you're applying a stress over a short time, you get a much higher value. This 10 is basically our 50-year value. 50 years is kind of an arbitrary. It doesn't mean the pipe fails at 50.1. It's just a point in time that we basically look at an intercept. So now, because we're looking at that extra time, we're now at 1,000 PSI. So when I test my material, it's actually 1,600 PSI. We then apply a 0.63 design factor that brings it down to 1,000. That 0.63 design factor basically looks at variation in my material because I don't make exactly the same thing from pellet to pellet. It looks at variation in Richard's extrusion process or any of our customers' extrusion process. And then it also takes into account typical installation issues. So as we showed when we were dragging that pipe around the corner, we're going to get some scratches to the material. There's going to be some stresses that are applied during the installation process. All of that basically backs it down. So we have reduced very conservatively the stress that the material could handle over a long period of time. And that's where we get that 1000 PSI that we start with as part of our design.
So everybody out there, all of you civil engineers, before this product even makes it to your yard, as to which you've bid the project and you've already come through this process, they have already factored in this massive conservation factor for you. The reason why it's different in natural gas than it is from municipalities is in natural gas, if you have a leak, people die, houses blow up, things like that happen. In the municipal world, it's not quite the same. However, this entire industry as a group is being extremely conservative for you already. When we start to look at ID matching and we start to look at all those things that happen when your alternate pipe material talks to you about HDPE, all those things are thrown out the window because this industry itself has already addressed that for you before it even the product ends up on your doorstep. So thank you very much, Doug, for being able to clarify that. We really appreciate it. Keep going.
All right. Thank you, Al. Next slide. Well, actually, one last thing on that slide. So up in the upper right-hand corner, you're going to see what looks kind of like little chocolate chips in the natural material. Most resin produced in the United States is natural material. We then add a carbon black master batch. That carbon black master batch gives you UV stability. So that's why we show this mix. So essentially, Richard is going to take my material, mix it with a carbon black master batch, and extrude black pipe. So that's just wanted to point that out. So we have built-in UV stability, unlike PVC. So in our case with black pipe, leave it out in the yard. Install it above ground. It's fine. It's got UV stability. It's the same UV stability that is used in telephone wires, which has been, we've had telephone wires up in the air for 60, 70 years. They work just fine. So just want to point that out. There are different classes of polyethylene. So if you go to the big box store and you want to install an irrigation system in your yard, you're probably getting a PE 1404 material. It's a very flexible material. It's not going to see pressure all the time. So it doesn't need as much pressure resistance as a distribution main would need. Our 2406 products, this is typically what's being used in the gas industry. This is yellow pipe. So it's a more flexible pipe, but it's also operated at significantly lower pressures, on the order of 5 PSI, maybe 50 PSI total. 3408s were the older high density polyethylenes, and now we're looking at the 4710. So as we have evolved the material, we have increased its ability to handle pressure. And as Alan talked about, we are now developed a new class of materials called low sag materials, all the benefits of PE 4710, but now we can make larger diameter pipe. So it's a great material, but it does fail. It fails long out in time, and it fails by what's called slow crack growth resistance, or a lack of resistance to slow crack growth. So if the pipe isn't properly installed, let's say we have it buried on top of a rock, or let's say we're doing a downhole application for geothermal and that pipe slips and now we've got it pinched against the concrete collar, we are going to induce a stress in the pipe wall. That stress will eventually cause the material to crack. Now hold on. When we developed the pent test, a lot of work was done in exhuming pipe from the field. And it was determined that 1 hour of pent resistance is equivalent to roughly 13 years of typical infield service. The 4710 resins have to have a minimum of 500 hours of pent. 500 times 13 is 6,500 years. Most of our pent values are actually in the 5,000 to 10,000 and above range. Does that mean that the pipe will last 130,000 years? I don't know. I won't be around to answer that question. It's probably an asymptotic, but what we are confident to say is 100-year design life is easily handled by these materials and likely longer. But legally, I can't tell you.
So one of the primary differences between the Alliance for PE Pipe, which shares a ton of knowledge, and other agencies is we'd love to talk about failure. In engineering, we actually learn more from failure than we do by success. It is painful to learn from your own failure. I will say very specifically that I have endured a significant amount of pain from learning from my own failures within my lifetime as a municipal engineer. And I share this with you, and Doug does as well, in order to be able to tell you about the pipe. So 50 years from an industry standpoint is a very conservative application. It's even beyond that. It's well beyond that. Most of the resin manufacturers probably won't say so from a legal liability, which you just heard. But you know, it is one hell of a product, and it certainly the benefits of installing it in that manner with the durability and the ruggedness is way better than what we're looking at. So, Doug, we got to kind of sort of advance.
Okay.
We got to go pretty quick. So let's make that happen.
Okay. Yes, sir. All right. Chlorine resistance. So polyethylene is affected by chlorine. Chlorine is present in potable water to neutralize viruses and bacteria. What we are concerned about is secondary disinfection. If you are using a system where your secondary disinfectant is chloramine or some type of free chlorine, be it chlorine gas, sodium hypochlorite, hypochlorous acid, whatever it might be, polyethylene, we know how to design for that. If that secondary disinfection is using chlorine dioxide, you really need to talk to your pipe manufacturer and understand. For the EPA, for free chlorine, the limit is between 0.2 ppm and 4 ppm. Chlorine levels dissipate as they work through the distribution system. So 4 would be at the distribution plant, 0.2 would be the end of the line. That way we have enough chlorine to disinfect the pipe. We have done a lot of work on chlorine. The earlier generation materials that had 1 hour, 3 hour, 10 hours of pent were more susceptible to chlorine resistance failures. We did a lot of work as the Plastics Pipe Institute in looking at small diameter and large diameter pipe in order to design and understand what happens to chlorine. So in most cases, and we'll see this on the next slide, chlorine is not going to be an issue in the distribution system. As we see here. So in average, even a CC2 material, which is not allowed in water piping, CC3, the maximum resistance is what is required by AWWA. In a typical average water system, you're going to get greater than 100 years of design life based off of chlorine resistance. If we talk about aggressive systems, these would typically be the Southwest United States, where we have shallow burial of the pipe, we have hot temperature in the soil. We are typically using a surface water system. More disinfection is needed. We are still looking at greater than 100 years of service life, design life with a CC2 material, and even more than that with a CC3 material. So this is all based off of exhumed materials. We have a very good idea what the design is. Where can I operate polyethylene? Well, polyethylene doesn't become brittle until -30 Fahrenheit. So pretty much anywhere on the planet, you can operate polyethylene and you can pick it up and you can bend it, and that material is not going to break. Unlike some of the other plastic materials that will. For example, an amorphous polymer is actually in its brittle state at room temperature. An amorphous would be a PVC material. So that's why you can put a hammer to polyethylene, but you don't want to put a hammer to PVC. Dave?
So the question comes up at what temperature can we actually perform bond fusion and join these pieces of pipe together? We can do that down to -4 degrees Fahrenheit. Typically, if we're below 32 degrees, we are going to come up with some way to mitigate the cold, whether working within a structure, mitigating wind, adding heat into a tent. But we can continue to fuse into some cold weather.
Yeah, generally, if your people are comfortable, you're going to be able to fuse from a temperature standpoint.
So I will
Yeah.
say it's about they are predicting snow in Florida, in northern Florida, and like basically everything is shut down. So if we're -40, people are generally going to be uncomfortable to begin with, let alone the pipe. But it's good to know that you know, if something like that happens, you put a heater up and you're ready to go in Wyoming or otherwise. So there you have it.
And a shameless plug for the Alliance, we have a recording on cold weather fusion, I believe, available on the YouTube channel where we talk about that. Richard, I'm going to hand the baton over to you, sir.
All right. Thank you very much. Of course, one of our greatest prides is the leak-free system that we're providing. We don't like leaks. We don't accept leaks, and we don't think that leaking is a good idea. So go to the next slide, please. So how does this happen? You know, if you start doing a comparison between metallic pipes and polyethylene pipes, there's corrosion. The corrosion aspects of polyethylene do not exist. Unless there's some type of chemical that is attacking the polymer, that's not really corrosion, but more attack or chemical attack. But you can see that legacy pipes do have corrosion issues. They also have tuberculation issues. Polyethylene not supporting any biological growth, and things don't really attach to it. It's almost like a Teflon type polymer where things don't really stick to it. You may have buildup of greases in a sewer system or things like that, but they can be easily removed because jetting is an aspect that will not affect the pipe at all. We did some experiments up to 5,000 psi and held it in one spot and tried to damage the pipe where it actually resisted. The water just bounces off of it. So there's a real aspect there from the sewer aspect that we don't have to worry about. The tuberculation aspect, you know, also affects your flow velocities and restrictions. And that corrosion also affects, you know, can support biological growth like we saw in Michigan. But the aspects of tuberculation are not a good thing for pipeline systems, and they affect pumping ability, they affect water quality, they affect your disinfectant efficiencies and everything about that. So we don't have to ever worry about that aspect. You can go to the next slide. Flexible and durability, we talked about. You could look at a PVC design in a cul-de-sac where we can loop it around fairly easily. If the guy didn't get the memo to get out of his, I guess, grass, I don't know if he parks his Ferrari on the grass or not, but anyways, we have the ability for efficient installations and durability. Now, it's not indestructible. I've had several inspectors call me and say, hey, I've got scratches on the pipe. This has happened, and we have ways to evaluate it. We encourage good installation practices or best practices, and those are available to you in the engineering and also in several PPI documents. Go ahead, David.
Yeah. So when in doubt, cut it out is one of the phrases that we use at the Alliance for PE pipe, and it's pretty simple to be able to cut that joint out or problem area out, and then you just simply fuse it back up. It's that simple. So Dave, you got something else?
Yeah, the flexibility of this pipe really minimizes the number of fittings that we need to add to the system. Really, unless a change in direction is made in a very short span, we can typically work with no more or no smaller than a 45-degree bend. We might do some 22s once in a while. We don't need to do 11s. The pipe will move. It'll handle those changes in terrain, whether they're vertical or launched or horizontal.
Excellent. And that's, that's a cost efficiency thing, right? And time of installation. So your bend radius, we understand the maximum bend radius. It's really based on DR. The thicker the wall, the more resistance you're going to have to bending. But as you get thinner in wall, you can kink. And you can see in the picture below, there was a large diameter that was kinked, so they exceeded that bend radius. But you can cut that out. That's not a big panic unless all the effusion equipment is gone already. But you can cut that out, refuse it, and then continue on. You don't have to panic about whether or not it's an outstanding issue. But that information is available. Establishing your pressure rating. One of the important aspects of establishing the pressure rating is really there's two factors. We evaluate polyethylenes at 73 degrees or 23 degrees Celsius or ambient temperature. But as we warm the pipe, of course, it's a thermoplastic, it'll absorb that heat. We can soften it. So if you have an application that you need to test at a higher temperature, then what we will do is you just derate that product based on these temperature compensating factors, which we have per degree Fahrenheit. So we can do that. Also, in association with that is your DR, or your wall thickness. The thicker in wall we go, the more pressure resistance that we have for that product. So this is the formula, plus environmental effects, which is not on this. The AF is the environmental effects. So in a lot of aspects where we supply gas industry pipe, if carbon contents or hydrocarbon contents get over 2%, then we have to derate it because there's a permeation effect. It doesn't destroy the polymer. It's just that hydrocarbon gets between the amorphous regions, and then we consider that an effect on the entanglement of that polymer. So we have to derate it a little bit. So you may have to go to either a thicker pipe or a lower DR, or just derate your pressure to accommodate that environmental effect. Yes, Alan.
So Richard, this is just additional information of our knowledge of the pipe itself. In the majority of applications for municipal installations, your buried installation is going to be well below the 73 degrees or stable at 73 degrees as we're seeing it. So you're not going to see a temperature fluctuation based on the installation temperature of the soil surrounding the pipe. It may, if you actually see large fluctuations in the conveyed fluid, which you need to pay attention to it. And then also from an environmental aspect, we're probably not going to recommend installing pipe in BTEX contamination. From an environmental engineer standpoint, we're going to recommend that you fix the contamination. If you have a BTEX contamination in an area, we're going to recommend that you remove that prior to installing any pipe. It's not just HDPE, it's going to be the gaskets of any bell and spigotted gasket pipe that's going to be, suspect to some type of installation in that manner. So this is just information to be able to provide you more from engineering standpoint. We're going to use our general principles to make sure that we put the right product in the right spot. So
that's correct, Alan. And just one aspect of that, understanding this formula is important for, I know there was a question on hydrotesting the product. So if you hydrotest above ground, you need to take into consideration if that pipe got really hot. Let's say you were on a typical warm day in Florida and that pipe was sitting out all day and it got warm and the fluid inside also got warm. You can still hydrotest it to 1.5 times if that's the number that you're testing at, but you just have to derate it in accordance to the temperature of that fluid and the condition of the pipe. You're still testing at that 1.5 times, but it just needs to be derated. And of course, with surge, high density polyethylene pipe has a high resistance to fatigue failure. So we need to understand what these surge effects are. We don't really typically fail in fatigue. So pressure up, pressure down, pressure up, pressure down, such as a surge effect. But we have at a working pressure, which is typically referred to as a reoccurring pressure of 2 times the pressure rating of that product. So whatever that DR is. So in a 335 DR7, that would be 670. And then that was for occasional. Sorry, I apologize. For a reoccurring surge, it's 1.5 times. So we derate that a little bit. So if your cyclic cycles are somewhere on average of 55 cycles a day in a water system in a utility, and that's a typical average for the U.S. by the way, then we would look at it as 1.5 times of the pressure rating to resist for the lifetime of that pipe. You can go to the next slide. So
Richard, I got a question for you.
Sure.
So we've received over 70 questions from the audience. I encourage you all to keep asking those questions. We are keeping up because we have a good solid bench today. One of the questions, Richard, had to do with intakes and outflows and rapid temperature changes of water as it's coming out of Lake Michigan. This is coming out of Holland. It uses polyethylene to heat their sidewalks so they don't have to shovel the snow. But their question relates to what resource should I go to learn how to restrain, if I need to restrain polyethylene with rapid water temperature effects?
Yeah, one of the things you can look at is the PE handbook, the PPI PE handbook, which has restraining aspects for those changes in temperature. We also have the S5 calculator, which is on the PPI website as well, which you can plug in your environmental conditions or your operating conditions to look at the stresses that are applied for temperature change. And then you can also look at the AWWA, which I think referenced back to the PPI calculator as well. You also have the PACE calculator, which can look at comparably under surge events and temperature effects, which you can have an input there to look at comparing the different products to those applications as well. So there are several resources. I'm not going to go into specifics with them, but if you need to go into specifics with them, you can contact me offline and we can work through your specific example.
You can also contact the Alliance for PE Pipe. We do have calculators and spreadsheets all set up for that as well. So we need to keep going, Richard. So let's just
we'll keep on
advance.
trucking. Yeah. So just on the last slide, we looked at magnitudes, look at different aspects. Just go back one quickly. Sorry, Alan. Yeah, so looking at the surge magnitude, the allowance, and the fatigue resistance is really important. So what we're saying here is we understand this phenomenon. Next slide, please. So looking at, again, the modulus of these materials that are typically used in water or municipal applications, there's always this aspect of understanding velocity of the material and the material's modulus in comparison to how it accepts these changes in magnitude. And so as you can see in the graph, the 4710 really doesn't have at 5 feet per second of velocity change in the pipes in various pipe sizes. It's quite a low number. So being very viscoelastic and ductile, you're actually dispersing and removing that energy away from that event occurring, so from getting worse. Whereas as you get into more rigid products, they tend to go higher in intensification. That's why you have limits on rigid pipes that you can have velocities for. And this is really important in your design because we really don't have a concern with your velocity change. It's just velocity. What we want to make sure that you're getting is in your design that you need that GPM at the end of the day that you require. Okay, you can go on to the next slide, please. So again, this is just pointing out in comparison what those pressure classes would look like. So with the reoccurring and occasional surges associated with them, and you can see that, we have a good resistance and we're very comparable to them, but especially in the pressure class, it really doesn't make any sense to me that pressure class is such an important value. Because really what you want at the end of the day, you need X amount of gallons per minute to source whatever you're sourcing. So the pressure class really doesn't come into play when surge pressure allowance is occurring. So you can see the differences between PVC, high density, and ductile iron in those aspects. Next slide, please.
So, Richard, while we're here and talking about this, most municipalities operate in the 55 to 75 psi range. And when we look at DR11, what is the pressure class of DR11?
200.
And then what is the occasional surge pressure class of DR11?
It would be 400.
All right. So 400 psi when we're looking at something that operates between 55 and 75 psi. And I will throw up my hands and say, the Super Bowl is one of those events as to which we have the largest demand on the sewer system and the potable water system. And we hope and pray that it doesn't break down during the Super Bowl, because that obviously is a problem for our crew when we're out there. But when we put all the pumps on and pumps off during a firefighting event, are we going to exceed this 400 psi pressure class of HDPE?
No, there's not a chance. Your velocities will change. Absolutely, your velocities will change, which will change the intensification of any kind of pressure surge event. So we have to have that resistance. I don't think when you start getting up to 400 psi, you have protection there on that occasional event, and that's very, very reassuring when it comes to putting out fires, of course, which California was experiencing, but they had a lot of other issues going on with that as well. So
we're not going to sidetrack. We're
no,
not going to talk about
but it's no, there is no problem at whatsoever. So even you could probably, I mean, we've been emphasizing the municipalities have incorporated a lot of the DR11 because of a safety aspect of that. More pressure resistance, so higher guarantee that nothing's going to fail. So we want to make sure that with fatigue, as that pipe expands and contracts, it's always going to be there. And we've tested that for 10 million cycles without failure. And so if you take 55 cycles per day, and you add it into or multiply that by 365, and how many years is that? You're not going to get anywhere near that 10 million cycles, where some of these other rigid products just don't meet that lifespan, just because it starts to fatigue those products to failure.
All right. So everybody out there, we have about 12 minutes left, and we're going to try to do as much as we can within the 12 minutes. Be aware that we have a YouTube channel that you can look at all sorts of different webinars that suit your need as you go through there. But this is an important discussion. Richard just said that there's 12 million cycles that they're testing this product to. It's huge. They're not testing it for potable water leaks. They're testing it for natural gas leaks, as to which when it leaks, it blows up and people die. So this is exactly what we want for municipal water in order to be able to have the rugged and durability that we need during installation. So we're protecting that product during installation in a manner as to which we're taking advantage of the fact that we're installing it in some type of fashion that gives us benefit. Not necessarily open cut. Trenchless gives us lots of great benefits. And then we're using the product that meets that need, and which is HDPE. So we're going to continue to talk about all this stuff. There's about 30 to 40 slides in trenchless or installation methods that we're probably not going to get to because we only have about 10 minutes more. However, we really appreciate you. We really appreciate the 81 questions that you've already thrown at us. Thank you so very much. That's kind of sort of why we're here, for all 650 plus of you. Richard, keep going.
All right, you can go to the next one, please. So fatigue resistance, we do have that resistance that becomes a limiting factor for some other products, which was already mentioned. There's 15 million cycles here. When we tested to GTI, it was 10 million cycles that we did do. Ductile iron, of course, is not factored into the design. You know, we don't really test for, or they don't test for these fatigue events, but they minimize their velocities to control that surge event from causing failure. So that limits your ability to pump. Now, I don't know if that's a factor in terms of the design of what your capabilities are for pumping, but that it's just not factored into that design. And again, for an amorphous material like PVC, it's limited to the operating pressure. Looking at the flow designs, we don't really have any issues. ID issues are a big concern that come out, but over time, and you can see this was a piece of pipe that was pulled 41 years after service with an electrofusion on it. I know there's a question about electrofusion integrity. If it's done correctly, it probably won't fail, but no buildup, whereas metal products do have that. And there are all kinds of calculations that we have to compare flow rates and everything to match these types of things. And let's say if you did a drill underneath a highway and you reduce the ID of the high density in there to match the OD of the existing or legacy products out there, all you're going to do is gain velocity in that section, which we're not concerned about. So if you went from 5 to 7 or 8 feet per second, and then as soon as it hits that open area on the other side of the open diameter, it's just going to slow right back down, but the volume will still remain the same. Permeation is a great question. It's a very common question where the BTEX materials, the hydrocarbons, the aromatics in the world do permeate the pipe. We have a calculator that you can look at, and I'm going to be dealing with that in another meeting tomorrow. We went through the calculations of a plume that was in the ground, and it was very, very low. I think it was below 0.006 parts per billion after exposure for X amount of time. But anyways, this is a calculator that Purdue University developed to understand that permeability. If it's greater than 2%, then you have to look at your pressure rating as well. Yes, Peter.
So I just want to ask Doug Keller to come on. We just got a question from a professor at Tufts about fires in polyethylene and PVC. And I think, Doug, we can answer both questions intelligently because we spent a lot of time studying this. And given what's been going on in Southern California, I think it's appropriate to talk, Doug, about the depths that these fires get to and what the impact on our infrastructure is. And specifically, I'm interested, Doug, after you give us the brief review on that, is the impact of benzenes and other chemicals that occur as a result of these fires on HDPE.
Okay. So when you have a forest fire or some type of a wildfire like we've had in California, most of the material that's being burned is plant matter. That plant matter is known to be a significant source of benzene. So when it combusts, benzene is released into the air. In some of the earlier wildfires that we had, Santa Rosa in particular, some of the houses on the top of the hill burned. The firefighters were pulling water, and they basically pulled a vacuum on those house connections and pulled combustion gas into the pipelines. When that gets in, that benzene will permeate, as we've talked about, polyethylene. So it is something that has to be considered. The U.S. Forest Service has done a lot of work looking at temperatures that the ground sees and the depth that temperature will penetrate in a wildfire. And in typical wildfire conditions, after about 2 to 3 centimeters, so 1 inch to 2 inches down into the ground, there's very little change in temperature. So a polyethylene pipeline that's properly buried with sufficient cover for that particular part of the country is not going to see significant temperatures. Now, at the end of it, where it may be exposed with a house connection or something like that, yes, you could see it. Polyethylene in a fire, when it burns, to have combustion, you have to have oxygen. polyethylene is going to produce carbon dioxide and water. It is the simplest reaction that is going to occur. Benzene is a very complex molecule that has to be formed in a non-oxygen environment. So polyethylene is not a source of benzene, but the benzene in the combustion gases can be drawn into the polyethylene, which means flushing may be necessary. Potentially replacement may be necessary, depending, typically if you're at the end of a trunk line, where you're not going to get sufficient flow.
All right,
So
that's a good explanation. I just wanted to go on the record with that, and that's absolutely accurate. So we appreciate that. Alan, sorry to delay Richard a little bit.
That's okay, Peter. I'm going to be rude and say that, environmental sensationalism over looking at an event such as this and casting doubt upon a pipe product when we have a complete travesty is incorrect and rude. And that's just part of what we're dealing with. Most of the time in traditional operations of HDPE pipe, withstanding natural environmental catastrophes such as we're seeing as this, it's more than used all the time. That's
and in fact, thank you for that, Alan. But in fact, in the campfire, Richard, you may remember what they do. They went back in and put polyethylene and PVC because they realized what was going on. All right, take it home, Richard.
All right, and then so these are the calculations that were used to understand. So there's a lot of inputs that are required for the contamination. If you did have a gas station plume in your city and you wanted to look through it, we could actually calculate what that looks like in terms of absorption into the water system and a moving water system. So we can take stagnant water or we can take flowable water, and you can get different values for that. But this is what it is. Poisson's effect, always a big concern during installation with polyethylene, because a lot of the times, like you saw in earlier pictures, the pipe sits above ground, it absorbs heat. We put it in the ground, it now relaxes, and we connect the lines and put everything and we bury it, and then we fire up the line. Then we get this expansion. We get this expansion of the polyethylene because we're applying hydrostatic stress to it, or the pressure. So it actually takes the forces and pushes it out. So it actually has a tendency to pull back on itself. So and make that line a little bit shorter. So we have to make sure, if we're connecting to legacy products, and this event is accommodated for, which we can calculate for, then we have to determine whether or not we need to protect the bell and spigot that we're attaching to. And a typical example of this is, again, we use high density in all these very difficult applications to drill underneath the roads so we can connect up to legacy products. And then we have to make sure we're protecting those legacy products against this Poisson's effect of expansion of the internal pressure that's being applied to the pipe. All right.
So we're at that spot now. I'm going to give you guys the contact information here for everybody. One of the coolest things about the Alliance for PE Pipes webinars that we give you is that you can talk to us at any point in time. We have lots of great people. Richard, stay on. We only have about 1 minute and 30 seconds. Doug and Peter, come on too. They love to talk about your projects. We absolutely love to talk about polyethylene being installed. Dave is one of those persons as well that's with us to be able to talk about polyethylene. Taylor, if he'll come back on as well. He's making polyethylene while we're talking now, so I'm not exactly certain if he's going to come back on or not. But making polyethylene is just as important as talking about polyethylene. But here we are. Please, let's have any resulting comments from the webinar.
Stephen Boros, did we get your email correct on there?
No, there's no dot after S, just S Boris.
Okay, sorry about that. Well,
Not
anyway,
a
Dave
problem.
Mosier, any closing comments, please?
Yeah, we're about to get to some things about quality assurance on the job site. So I'm more than happy to discuss that with anybody, how we can build quality assurance into your specification and your installation.
Awesome. Taylor Holiday.
Yeah, just want to reiterate how important it is to pay attention to what you're seeing manufactured. It was brought up about the print line. I think that is probably one of the most significant points that was brought up from a manufacturing standpoint of HDPE pipe is make sure you see the print line.
Good. Hey, great job, team. And I want a particular thank you to all our guests for hanging around to the bitter end. 75 minutes of a lot of content. We've been very patient. We had over 80 questions. And please take a snapshot of the screen that's on right now so that you know the email address of the individual you want to contact. It looks like we've corrected Stephen Boros's email address, and also Doug Keller's is douglas.keller. Sorry about that. And we'll see you shortly with our next webinar. Thank you to Core & Main and Modern Polymer. We'll see you in 2 weeks.
Thank you, everyone.
Bye for now.
Bye-bye.
Bye-bye.